Today, we're talking about section 2.2, and 2.2 is about more graphs and displays. So, there are tons of displays for statistical information. Think of the ones we've already encountered. And you may not think we've talked about a lot of graphs, but in 2.1, we actually came up with quite a few different displays for statistical information. They're not all graphs, but they are all displays. The first was the frequency distribution. After that, we learned about frequency histograms. Then we talked about frequency polygons, relative frequency histograms, and then ogives. So we've already gotten 5 different displays or graphs of data, but there are a lot more. So these displays are great, but one of their drawbacks is that they only deal with quantitative data. There's no place for qualitative data on these particular graphs. So we need some displays that can incorporate qualitative data as well. But before we get into those that incorporate qualitative information, we need to talk about a few more quantitative displays first. The first one is called the stem and leaf plot. So what a stem and leaf plot is it's a visual display that splits each data entry into 2 parts, the last digit, which we call the leaf, and the first part of the number, which we call the stem. So if a number is 10 digits long, the last digit of the number is the leaf, and the other 9 digits of the number are the stem. So what's the process? Well, first thing you're going to do is split data values into 2 parts, the last digit and the rest. So, for instance, if you had a data value of 156, then the stem would be 15 and the leaf would be 6. The leaf is always a single digit. The stem can be multiple digits, but the leaf is always a single digit. We're going to do that for every data value. So if your data set has 40 data values, you're going to split 40 data values just like this. Next, you're going to write all of the possible stems, beginning with the smallest and ending with the largest. You're going to arrange them vertically. You're going to include all stems between the smallest and the largest, even if they have no leaves. What does that mean? Well, if your minimum stem is 11 and your maximum stem is 24, then you're going to write all of the stems between 11 and 24. All of those numbers, so 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, regardless of whether there's any data values that have those stems. So whatever your smallest stem is and your largest stem is, you're going to write every number between those vertically, even if there are no data values that have those particular stems. And you're going to place all stems in order on one side of a vertical line. Then you place all the leaves on the other side of the vertical line across from their stems, and the leaves can be ordered or not. Now, when you look at a process like this on paper, it all sounds very complicated. A 7-step process, we're splitting numbers, stems, leaves, putting them in certain orders, incorporating stems that don't exist. But in actuality, when you start to do this process, it's pretty straightforward. So we are going to look at an example. Consider this data set. So we have 30 data entries here, and we want to try to build a stem and leaf plot. So what we're going to do is we're going to find the maximum and the minimum values. That's going to help us in this process. So the maximum value for this data set is 102. The minimum value is 23. So that means when I write my stem and leaf plot, I'm going to have a 2 for a stem and a 10 for a stem. And I'm going to have to write every stem, every number between those 2 values. So we're going to place all those stems on the left side of a vertical line. So we'll keep the data set up there in the upper right hand side so that we can refer to it. And notice, I started at 2, which was my minimum stem. I went to 10, which was my maximum, and I put all the numbers between 2 and 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I don't know if there's going to be data values for all those. All I know is that I have my minimum and I have my maximum and every number between. So then we sort through this data and put the correct leaves with the correct stems. So we'll start with 25. 25 would have a stem of 2 and a leaf of 5. So across from the 2 on the other side of the line, we put a 5. 42 has a stem of 4 and a leaf of 2. So across from the stem of 4 on the other side of the line, we put 2. 61 has a stem of 6 and a leaf of 1. So we go to where the 6 is and we put a 1 on the other side of the line. 53, so we've got 5 on the other side of the line, 3. 65, so where the 6 is on the other side of the line, we put a 5. Now we've already got a 1 over there, so we just go over a little more space. There's no commas. Do not put commas in a stem and leaf plot. Next we have 44. So again, after the 2, I'm going to leave some space and put the 4. 29. So I leave some space after the 5 and put the 9. 57. After the 3, I put the 7. 69. So now that row is 1, 5, 9. Again, no commas. 102. Then the next row of data, 51. 23. 57. 74. 40. 52, 58, 61, 29, 54, 69, 45, 43, 79, 73, 64, 48, 60, 59, and 70. So this is the unordered stem and leaf plot. Why is it unordered? Well, because when you look at the leaves are not in numeric order. They don't go from smallest to largest. So one of the things that we want to be able to do is create an ordered stem and leaf plot. So to create an ordered stem and leaf plot, then what we're going to do is we're going to rearrange each row of that stem and leaf plot to put those numbers in numerical order. So for instance, the top row that is currently 5, 9, 3, 9, we go from smallest to largest, so that would be 3, 5, 9, 9, if we put it in order. And so the ordered version here, if we went through each row and did that, we'd have the 3, 5, 9, 9. The third row would be 0, 2, 3, 4, 5, 8. The row for a stem of 5 would be 1, 2, 3, 4, 7, 7, 8, 9. When the stem is 6, the row would be 0, 1, 1, 4, 5, 9, 9. When the stem is 7, it would be 0, 3, 4, 9. And on the stem of 10, it's just a 2. On exams, on quizzes, we'll always be asking for the ordered stem and leaf plot. What can we tell from a stem and leaf plot? Well, look here. We know there's no data in the 30s, none in the 80s or in the 90s. We can also see kind of how the data is dispersed. We see that 102 seems odd because it's kind of away from the rest of the data. So there are lots of ideas that we can glean by looking at a stem and leaf plot. So what are the actual features? Well, first, it's similar to a histogram. If you turn it on its side, then the way that we have those numbers aligned, they look like the bars in a histogram. More leaves equals a higher bar. They still contain all of the original data values. So one of the drawbacks of a histogram is that we can't see the data values anymore. But in a stem and leaf plot, we still can. It helps us sort the data. We actually took a 30 individual data set and put it in order when we switched from the unordered to the ordered version of the stem and leaf plot. And oftentimes we need to find an ordered data set to do some of the things that we're going to do. It's a very compact way to express the data. If we have a bunch of numbers in the 60s, we write the 6 just one time and then all of the second digits. So we stop writing those extraneous stems over and over and over again. And lastly, it helps us to identify outliers. So there's a natural question that comes, what's an outlier? Right? We haven't talked about that yet. So let's define what an outlier is for us. These are unusual data values that are set apart from the others. So on that example we just did, 102 seemed to be kind of far away from all the other data values. It didn't look like the other data values. It was different. Now that's not a very mathematical definition because we use a phrase like they're set apart from the others. And in math we like to be fairly precise. How far apart does it have to be before it's considered an outlier? Right? How far away from those other data values? And we're not quite ready to answer that question because we need a few more concepts. We'll actually give a more precise definition in section 2.5. But for right now, just realize that it is there on the horizon and that these outliers are kind of far removed from other data values. So now it's time for a practice problem. Consider this data set. We have 40 data entries here. And I would like you to create an ordered stem and leaf plot. So give yourself a little bit of time to do this. Press pause on the video, and when you're all ready to see the answer, press play. Okay, so here's our solution. We're not going to go through it like we did the other one. The unordered version, if you just went row by row, you would have stems ranging from 2 to 8. So you would write 2, 3, 4, 5, 6, 7, 8. So you have those stems arranged vertically on the left side of a vertical line. And then we place our leaves on the other side. So the only leaf on the stem of 2 is 7. Then for 3 we have 1, 9, 0, 8, 1, 2, 1, 0. For 4, 7, 9, 9, 0, 1, 0, 8, 2, 3, 2, 9. For a stem of 5, the leaves are 1, 8, 7, 1, 2, 7, 9, 6, 4, 2, 7. For the stem of 6, we have 4, 5, 5, 5, 4, 8, 1. For the stem of 7, there are no leaves. And then for the stem of 8, we have 8 and 2. But remember, our question was to create the ordered stem and leaf plot. So the ordered version, we're going to rearrange those leaves to put them in numerical order. So we're going to have 2 followed by 7. The stem of 3 has 0, 0, 1, 1, 1, 2, 8, 9. For the stem of 4, it's 0, 0, 1, 2, 2, 3, 7, 8, 9, 9, 9. When the stem is 5, we have 1, 1, 2, 2, 4, 6, 7, 7, 7, 8, 9. When the stem is 6, we have 1, 4, 4, 5, 5, 5, 8. And then for the stem of 8, we have 2 and 8. So that would be the ordered version. One mistake that students make is they try to look at the data set and put it in order from the beginning. That takes an awfully long time. The easiest thing to do is to just make an unordered stem and leaf plot and then reorder those leaves. If you try to find the data values in order, it takes much more time to do, and you'll find out that it wastes your time. So just make the unordered version and rearrange the numbers, and you'll end up being a lot happier. Okay, so there's a second type of stem and leaf plot We're not going to see it too much, but every once in a while you'll run into it. And instead of writing each stem once, you write each stem twice. And then we arrange our leaves so that the leaves from 0 to 4 are on the first stem for a number, and the leaves from 5 to 9 are on the second stem for that number. So we're just going to convert one of the ones we've already done and put it in this format and see how it looks. So now it's time for an example here to show that double-stemmed variety of the stem and leaf plot. Recall the stem and leaf plot we came up with as the answer to the practice problem. Convert it to a double-stemmed variety. So this was that ordered stem and leaf plot we just did. What's going to happen now, instead of our stems being 2, 3, 4, 5, 6, 7, 8, we're going to write each stem twice. So it's going to be 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. And then on the first stem for any particular number, we are going to write the leaves from 0 to 4. And on the second stem, we're going to write the leaves from 5 to 9. So when we're all done with that process, the stem and leaf plot we get looks like this. So notice, 2 stems for each stem, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. But now what we've done is we have rearranged our leaves so that the leaves from 0 to 4 are on the first stem for a particular value, and that the leaves from 5 to 9 are on the second stem for that value. So look at the 3s. We have 0, 0, 1, 1, 1, 2. Those are all between 0 and 4. And then on the second 3, we have 8 and 9, which would fall between 5 and 9. So basically, we're splitting them up into smaller chunks. The stem and leaf plot splits values up by tens. So it splits up values by the 30s and the 40s and the 50s and the 60s. What this version of the stem and leaf plot does is it splits it up by 5s. So you have 20 to 24 and 25 to 29, 30 to 34, 35 to 39, 40 to 44, 45 to 49. So it's just a smaller arrangement of the data values. Instead of looking at them in groups of 10, we're looking at them by groups of 5. Okay. So another display that's kind of useful is called a dot plot. It consists of 2 things, a number line containing all the data values, and then a dot above each data value in our data set. If a particular data value appears multiple times in our data set, then there will be multiple dots. Those dots will be stacked on top of each other. So let's see how that works. For example, consider this data set. So we have these 30 data values. We want to create a dot plot. So what we're going to do, we've got our number line here. Here's our data set. And we're just going to go entry by entry, placing a dot where it belongs. So the first data entry is 53. So at 53, I put a dot. 65, I put a dot. 42, dot. 55, dot. 61, dot. 63, dot. 43, dot. 53, that's our second 53, so we stack that dot. 47, dot. 42, dot. So we've got a couple that are stacked now. 49, dot. 51, dot. 47, another stack. 61, 53, 47, 55, 64, 65, 53, 52, 48, 53, 55, 65, 42, 53, 48, 47, 49. So that's our dot plot for this particular problem. And what does it do for us? Well, just like the stem and leaf plot, we just put the data set in order. Because now we know that the data set in order would be 42, 42, 42, 43, 47, 47, 47, 47, 48, 48, 49, 49, 51, 52, 53, 53, 53, 53, 53, 53, 55, 55, 55, 61, 61, 63, 64, 65, 65, and 65. So the dot plot puts them in order. It also helps us find the mode. When we talk about mean, median, and mode, this helps us find the mode of the data, which is the most frequently occurring data value. We'll discuss that further in a later section. And so this is very useful to us as well for ordering the data set. So now we're going to see a bunch of other displays that might seem familiar to you. We'll start with a pie chart. What a pie chart is it's a circular representation of results where each different result is assigned to a wedge in the circle whose size is proportional to the size in the sample. There are some rules to construct a pie chart. First, you got to draw your circle. So for each qualitative data entry, you're going to create a fraction. And what that fraction is the numerator is the number of data values in a particular category, and the denominator is the total number of data values in your study. You're going to multiply the fraction for each entry to 360 degrees, and that's going to give you the central angle of each wedge for your pie chart. You're also going to multiply the fraction for each entry to 100, and that is the percentage that each wedge represents in your pie chart. So let's take a look at one of these. For example, a survey is administered to a group of 120 people. They are asked how they like to spend their free time. The results are in the table below. Create a pie chart. So these people like to go on Facebook. 45 of them said they do that. 20 of them said they like exercising. 30 of them said they like to go web surfing, so kind of kicking around the internet. And then the other 25 indicated that their favorite activity to do was reading. So we're going to try to put all of this in a pie chart. So we need to add up the total number of responses. 45 and 20 is 65, plus 30 is 95, plus 25 is 120. We knew there were 120 because we were told that in the original problem, but it's always a good idea to double check. Now we're ready to create our fractions. So we'll start with Facebook. Remember how we created the fraction? We said it's the number of data values in the category in the numerator and the total number of data values in the denominator. So for Facebook, that's going to be 45 over 120. What we do with that 45 over 120, it actually reduces to 3 over 8. We can multiply that to 360 degrees, and that gives us 135 degrees. That's going to be the angle at the middle of the pie chart for that particular wedge in that chart. Then we multiply the 3/8 times 100%. We get 37.5%. That's how much of the pie chart it takes up. Because if you think about pie charts that you've seen, they always show not only what category is in each wedge, but also the percentage that that category represents. So that's why we multiply it to 100% as well, for us to find that percentage. Let's look at exercising. Exercising would be 20 over 120, which reduces to 1/6. So we get 1/6 times 360 degrees, which is 60 degrees, and 1/6 times 100%, which is 16.67% if we round to 2 decimal places. Then for web surfing, the number of responses is 30, so we get 30 over 120, which is 1/4. So 1/4 times 360 degrees is 90 degrees, and 1/4 times 100% is 25%. And then for reading, We get 25 over 120, which is 5/24. We multiply that by 360 degrees, we get 75 degrees. And when we multiply it times 100%, we get 20.83%. What you should notice is that all four of the degree values, 135, 60, 90, and 75, add up to 360 degrees, which is the total number of degrees in a circle, and that the 4% values, 37.5, 16.67, 25, and 20.83, add up to 100%. So that tells us we are doing this correctly. So now let's see how we put that on our pie chart. So we have 135 degrees, 60 degrees, 90 degrees, and 75 degrees. So when you look at this circle that we're going to build our pie chart in, it looks like spokes on a wheel. And what those spokes represent is their 15-degree increments. So that's going to make it easier for us to figure out where exactly we put the lines for our pie chart. So the first measurement was 135 degrees. And so I'm going to start from the top vertical line and measure. And when we do 135 degrees, we start at this top and we go down 15, 30, 45, 60, 75, 90, 105, 120, 135 degrees. So this area here would be 135 degrees. Let's go ahead and get rid of the spokes in that area to clean it up a little bit. And so now we have our first wedge. When I build these, I always do the next largest wedge. I don't necessarily do the one that comes next on the list. So my next largest wedge was 90. I'm going to start at the top again, but I'm going to go the other way. So that gives me 15, 30, 45, 60, 75, and 90. So I'm going to go ahead and bold in this line here. And then let's clean it up. So that's the second wedge. Then we have wedges of 60 and 75. So let's go ahead and in the remaining section, let's go ahead and put those two wedges. One line will build both wedges. So you can see that this is 15, 30, 45, 60 degrees. And what's left here is 15, 30, 45, 60, and 75 degrees. So if we go ahead and clean those up, now we have the four wedges representing those four pieces of the pie chart. Let's go ahead and put some color on this. Most of the time you see pie charts, the wedges are colored. On a test, I wouldn't expect you to color the wedges, just to have those wedges defined. And now we need to label these so that if a reader is looking at this pie chart, they know what it refers to. So that first orange wedge, the largest wedge, refers to Facebook. The second largest wedge was web surfing. Then the smallest wedge was exercising. And the bottom wedge represented reading. We also need to incorporate the percentages for each one of those. For Facebook, it was 37.5%. For web surfing, it was 25%. Exercising was 16.67%. And reading was 20.83%. So that's how you actually build a pie chart. Most people just think you draw a random circle and throw in some wedges and then label them. But they actually have to be measured wedges. They have to relate to the size of that set. So the larger the particular category is, the larger the wedge should be. And there's a formula to derive how to do that based on taking the fraction that we create and multiplying it times 360 degrees. That's how we find the size of the wedge. So the next type of graph is called a Pareto chart, and it's a bar graph. Remember, we've done a bar graph called a histogram, but this bar graph is significantly different. First, the horizontal axis on a Pareto chart has qualitative labels. In case you didn't realize it, when we were talking about the pie chart, that's a qualitative graph. There's qualitative information on it. The names of the categories appeared on the graph, and that's the first time we've seen qualitative information on a graph. This Pareto chart is another instance where we will see the qualitative information. The vertical axis represents the frequency measurement. And when we draw a Pareto chart, the bars have to go from tallest to shortest. And those bars don't touch. In a histogram, bars do touch. In a Pareto chart, bars do not touch. So here's an example. We're going to use that same data from the pie chart, but now we're going to build a Pareto chart. Okay. So let's go ahead and see how that looks. Now you notice I have some wide bars and some skinny bars. And the reason that I do that here vertically is because I want to leave space between my bars. So the wide bars are where the bars for my Pareto chart are going to be, and the thin columns are the spaces between the columns. So on that example with the exercising in Facebook, the tallest bar should be Facebook because that had the most number of responses. Facebook had 45 responses. So I'm going to build my first bar to go up to 45. I'm going to leave some space and then build my second bar. The second highest category was web surfing, and web surfing had 30 responses. So we'll build a bar that goes up to 30. The next was reading, which had 25 responses. And last, exercising, which had 20. So we can go ahead and clear out those bars there, and we'll add in some color, just like we did with the pie chart. And then we put labels on the horizontal axis. So the green bar represented Facebook, the highest bar was Facebook. Then web surfing for the next bar, reading for the third bar, and exercising for the last bar. So you can see that these bars go from tallest to smallest, from left to right. Pareto charts must always go from tallest to smallest. So this has the exact same information as the pie chart, just expressed in a different manner. Now you have to be careful with Pareto charts because the frequency scale in a Pareto chart can be intentionally misleading. So one of the reasons that stats is a course that a lot of people take is because there's so much statistical information presented to us in society. We see it all the time, books, magazines, we see it on television, it's kind of everywhere. And we want to be critical thinkers whenever we see statistical information presented to us because we don't want to fall for any gimmicks based on poor presentation. So what do I mean by that? Well, here's a Pareto chart for that same data that we just did. So you'll see that Facebook goes up to 45, web surfing goes up to 30, reading goes up to 25, exercising goes up to 20. So this has all the same information as the original Pareto chart, but this one is built in a way that can be misleading to people. Why could it be misleading? Well, when we look at these bars, like look at the exercising bar, doesn't the reading bar look twice as tall as the exercising bar? It does, but if you remember right, the number of people who were readers was not twice as large as the number who were exercising. It was 20 and 25. But by changing the scale here, we've made it appear visually as if the number of people who read is twice as many as the number of people who exercise. So that's why this is misleading. It's because it contains the same frequency information, but because we've limited the range of the vertical axis, the relative size of the categories is visually distorted. Most people, when they read, they just glance at tables and graphs like this. They don't pay really close attention, and their mind sees, oh, that bar's twice as big. And you might get that in your head that that reading category is twice as much as the exercise category because all you did was look at it visually. You didn't actually dissect it and look at it analytically to try to see what information was presented. So oftentimes, especially advertisers, will build graphs like this to try to mislead people. They can say, look, I put all the information on the graph, which is absolutely true, but the way in which they put that information misled people. You can't get in trouble for it because you didn't lie. All the information in the graph is absolutely true, but you've built the graph in such a way to mislead people visually. And so it's a little bit underhanded, but it happens all the time. And one of the reasons we want you to take a class like this is so that you can be aware that those kinds of things happen and that you should always look analytically at things to try to decide what information is actually present. So next we have different types of graphs, and these graphs deal with paired data sets. Paired data sets will have two quantitative components. So oftentimes you'll have linked values of some sort. So for instance, if you were tracking sales for a business over a period of time, you might have a year and a dollar figure that are paired together. So those would be paired data values. And whenever we talk about paired data values, we have two different types of graphs that we use. We have scatter plots and time series charts. So let's start by talking about scatter plots. What is a scatter plot? Well, it's exactly what it sounds like. We just graph individual data values on a graph, and the result looks like a bunch of dots scattered around our graph. So let's see one. Here's our example. We have measured the height and weight of all 15 students in a preschool. The results are in the table below. Create a scatter plot. So we have their height and weight. So one of the children was 36 inches tall and weighed 41 pounds. So you can see how these would be linked, right? Because each pair represents one person, the height and the weight for that person. We had a child that was 34 inches and weighed 37 pounds. Another child that was 38 inches and weighed 37 pounds. Then a 37-inch tall child that weighed 42 pounds. And so on and so forth through all of this data. We have all 15 of these values. What we want to do is put them on a scatter plot. So what we're going to do is we're going to create a coordinate plane that has the horizontal axis corresponding to the height and the vertical axis corresponding to the weight. And then you're going to plot each point. So I've put all of those ordered pairs for height, comma, weight along the side of this graph so that we can see them as we're graphing. And we will start with 3641. So we're going to put a point 36 spaces over, 41 spaces up. So that's our first point, 3641. Then 3437. Then 3837. 3742. 4144. 3536. 3733. 3639. And 4040. Then 3538. 3233. 3835. 3936. 3836. And 3539. So that's our complete scatter plot for this problem. If we look at this in the context of the problem, these represented children at a preschool, then what we see is on this graph in the bottom left, we have this individual who was 32 inches tall and 33 pounds. That is the smallest child at the preschool. Then at the top right, we have a student that was 41 inches tall and 44 pounds. This would be the largest child at the preschool. And those smallest and largest child, those two children, they tend to kind of be away from the center of the data. So they might be outliers. They might not, because we haven't actually defined what it means to be an outlier yet. But those would be candidates for being an outlier because They kind of are away from the central cluster of data, which is all kind of here together in the middle. We also seem to have a low value here at 37, 33, so that could also be an outlier. After scatter plots, we want to talk about time series charts. So what is a time series chart? Well, a time series chart graph values over time. The displays are prevalent in the media. We see them all the time when we're talking about unemployment rates, home foreclosures, stock prices. When you see graphs like that, then you're probably talking about a time series chart. So how do you build one? Well, the horizontal axis on your graph is going to represent time. The vertical axis is going to be your measured data value. And then you're going to connect successive time points with straight lines. Okay, so let's look at an example. Gross sales for a company are recorded over a 10-year period. The results are in the table below. Create a time series chart. So for this particular company, in 2001, they had $3.1 million in sales. In 2002, 3.3 million. 2003, 3.2 million. 2004, 3.5 million. 2005, 3.9 million. 2006, 3.7 million. 2007, 4.2 million. 2008, 3.4 million. 2009, 3.5 million. And 2010, 3.7 million. So to arrange that information on a graph, we're going to plot each one of those points. So I've put these points on the graph. You can see in 2001 we had 3.1 million. In 2002, 3.3 million. 2003, 3.2 million, and so on. But once we've got these points, we're supposed to connect successive time points with straight lines. So because we were measuring by years, we go by successive years and connect those points. So 2001 will connect to 2002. 2002 will connect to 2003, 2003 to 2004, and so on. And when we do that, we get a graph that looks like this. That's what a time series chart will look like. If you've ever seen a news show that talks about the stock market, you'll see graphs like this where they talk about how the stocks go up and down, or unemployment rates, how they go up and down. You see these kinds of graphs all the time in business. So time series charts are used a lot in business. And that's the last graph that we're going to talk about in this section. So that brings us to an end of section 2.2. Please look at Pearson for your homework and have a great day.